Okay, so we will start with the linear transformation, or it is also called linear mapping between two vector space. So, basically we have two vector space u and v, say u and v over the same field f. So, that is required. So, u v are two vector space over the same field, and a mapping from u to v is called a linear mapping or linear transformation if the following conditions satisfy. There are two conditions: if T of alpha beta is equal to T of alpha plus T of beta. So, we take two alpha beta from here, alpha beta. So, and this must true for, and T of alpha beta, say this one. Now, T, this is T alpha, this is say T beta, it could be same also, and this is basically T of alpha beta, and this should be equal to T of alpha plus T beta, and this was true for all such alpha beta. This is one condition. So, for all alpha beta belongs to U. So, this is a linear property. Now, we have with scalar T of A alpha is equal to A T alpha, and this must true for all A scalar and for all vector from U. Okay. So, that is the reason we should have a same field, because T of alpha is a element in V, and if we are not having same field, then we cannot just multiply A with, this is a scalar multiplication in V. So, this must be satisfied. So, combining these two, so if these two conditions is satisfied for a mapping from U to V, then the mapping is called linear mapping or linear transformation. In short, it is called LT. Now, to combine these two property, we can just write in a single property. So, instead of these two, we can just write T of A alpha plus B beta if this is same as A T alpha plus B T beta, and if it is true for all A B scalar and for all alpha beta vector, then we call this mapping is a linear mapping or linear transformation. Just we are combining, we take for first condition we need to take A and B to be the identity element from the field, and second condition we take B to be the 0 and A is this. So, these two, either we take these two condition or we take only in single condition, and this must true for all scalar A B and all vector alpha beta from U. So, if this is satisfying, then we called a linear transformation to be linear, then we call this mapping T to be a linear transformation or linear mapping. Okay, but this U V has to be from the vector space over the same field. U and V are the vector space over the same field. Okay, now we will take some example of linear transformation. So, let us take some example of linear transformation. Okay, suppose we consider the vector space R 3. So, we defined a mapping from R 3 to R 3 like this. So, T of x 1, x 2, x 3. So, R 3 is the, R is the set of real number. So, if we define like this, x 1 plus x 2 plus x 3 is the first, then 2 x 1 plus x 2 plus 2 x 3, then x 1 plus 2 x 2 plus x 3. Okay. So, if we have this transformation, then we are going to show that this is a linear transformation from R 3 to R 3. So, to show this we have to take 2 alpha beta from here. So, we take alpha say x 1 x 2 x 3 and beta is say y 1 y 2 y 3. So, basically what we need to show? We need to show T of A alpha plus B beta, where A B are two scalar. Scalar means this is over the real field, a real field. So, scalar means here real numbers. So, this we have to show this A T alpha plus B T beta. Okay. So, if we can prove that, and if we can prove this is for all A B and for all alpha beta, then we are done. Alpha beta from R 3 for all A B from R. This we can try. I mean, it just we have to take this what is. So, what is basically A alpha plus B beta, this is nothing but A x 1 plus B y 1 comma A x 2 plus B y 2 comma A x 3 plus B y 3. So, if we take the transfer, so we can take this as a z 1, z 2, z 3 by taking this. Then, if we take the transformation on this T of this thing. So, this is z 1 comma z 2 plus z 3. We know by definition this is z 1 plus z 2 plus z 3 comma 2 z 1 plus z 2 plus 2 z 3 comma z 1 plus 2 z 2 plus z 3. Now, if we put the value of z 1, z 2, z 3, we can easily show that this is nothing but A T of x 1, x 2, x 3 plus B T of y 1, y 2, y 3. So, this is nothing but A T alpha plus B of T beta. This one has to verify this. Okay. Just a simple calculation will give us this. So, this we have to little bit work out on the exercise book. So, you can achieve this. So, this is basically a linear transformation. This is a linear transformation from R 3 to R 3. Okay. So, now we will take an example where the transformation or mapping is not a linear. So, say for R 3 to R 3. So, we take this to be say x 1 plus 1, x 2 plus 1, x 3 plus 1. This is also a mapping from R 3 to R 3. Now, we will see this is not a linear transformation, because if we take alpha to be x 1, x 2, x 3 and beta to be y 1, y 2, y 3, then T of alpha plus beta is basically x 1, x 2, x 3 plus y 1, y 2, y 3. So, T of this. So, T of alpha plus beta is nothing but what? So, T of x 1 plus y 1. So, this is basically x 1 plus y 1 plus 1, x 2 plus y 2 plus 1, comma x 3 plus y 3 plus 1. So, this is equal to x 1, x 2, x 3 plus y 1, y 2, y 3 plus 1, 1, 1. So, this is not same as T of alpha plus T of beta. So, to be a linear transformation, this has to be T of alpha plus T of beta. So, this is an example where this mapping is not a linear mapping. Okay. So, we can take another example also from say R 3 to R 4. So, R3 to R4, how we are defining this mapping? So, T of x1, x2, x3 to be, okay. So, this is basically x2 plus x3 comma x3 plus x1 comma x1 plus x2 comma x1 plus x2 plus x3. So, this is 4 dimensional. Okay. Now, I leave as an exercise to you that to show this is a linear transformation. So, basically we need to take 2 alpha beta x1 x2 x3, beta is equal to y1 y2 y3. Then we need to show that T of A alpha plus B beta is equal to A, okay, for any two real number A B. So, if we can show this, then we are done. So, this I leave as exercise. So, this is a linear transformation from R2 to R3 to R4. Okay. So, now we will define, we have some properties of the linear transformation. So, the first properties is, suppose we have a linear transformation from U to V. So, this is, we have two vector space U and we have another vector space V over the same field F. Okay. So, we have a mapping from here to here, we have alpha is mapped to T alpha. So, this is a mapping from U to V, and to suppose this mapping is a linear transformation or linear mapping. Now, this theorem is telling there are two parts. One is this 0 vector 0 of U, 0 vector of U is mapping to 0 vector of V. Okay. So, this is telling us that T of U is basically V. So, 0 vector should map to the 0 vector. Okay. How to prove that? So, to prove this, we take 0 plus 0 is 0 because this is the identity element. We know the vector space means that it is abelian group under plus. So, this is the identity element. So, 0 plus 0 we can write this 0. Now, we take linear transformation on this. So, this is T of, okay. Now, since T is linear, so this is T of 0 u plus T of 0 u plus equal to T of 0 u. Okay. Now, if we subtract T of 0 u from both sides and we use the associativity law of this plus, then we get that we take T of 0 u minus T of 0 u both sides plus T of 0 u is equal to minus T of 0 u plus T of 0 u. So, this by association law this will cancel out and then this will give us a, so T of 0 u nothing but 0 v. So, the 0 vector is going to the 0 vector of the other vector space. Okay. This is one property. Another property is that alpha. So, this is the second property, T of minus alpha is equal to minus of T alpha. Again we can prove this by this way. So, we take alpha. So, alpha plus of minus alpha, we know this is the 0 vector of u. Now, we take the transformation on this. So, this is linear. So, T of this plus T of minus alpha is equal to T of this. Now, just now we have seen this is T of v. So, this implies T of minus alpha is equal to minus of alpha. this is another result. Okay. So, these are very this we can say these are the result, these are the properties of a linear transformation from a one vector space to another vector space. Okay. So, now we will define a kernel of a vector space. So, kernel of a linear transformation, sorry. So, suppose we have a linear transformation from U to V, same thing, we have a two vector space U and V over the same field. Okay. So, we define kernel of T, and suppose this is a linear transformation. Kernel of T is basically set of all vector from U such that they are mapping to 0 vector of V. So, it is basically the set which are all mapping to the 0 vector of. So, this is the 0 vector of V. So, these are all, this set is, in short it is written as car, CER, KER, car of T, kernel of T. Okay. So, now this kernel of T is not empty. Why? This T is not empty, because we know theta 0 vector of U is there, because just now we have seen T of this is basically going to this. So, at least this belongs to kernel of T. So, this means this is not empty. So, at least this 0 vector is a member of this 0 vector of U. Okay. So, now we will have we will see some properties of this kernel. First of all, we will see the kernel is a subset of U. Now, we will see this kernel is a subspace of this vector space. So, how to prove that? So, this is again by the theorem we will prove kernel of T is a subspace of U. Okay. So, this subset is again from a vector space under the same over the same field. So, how to prove that subspace? So, for proving the subspace we know that we have to take two elements alpha beta from that subset, and if we can show that A alpha plus B beta is belongs to that subset, and if that is true for all A B, and if this is true for all alpha beta, then we have proved a theorem from which we can say this is a subspace of U. So, now we have to show this. So, let us try that. So, we take alpha beta from, let us remove this. Okay. So, we take alpha beta from the kernel of T. So, this implies T alpha is equal to T beta is equal to, they are mapping to 0 vector of V. That is the definition of kernel. Kernel consists of all the vectors in U which are mapping to 0 vector of V. Okay. So, now we take this A alpha plus B beta for any given alpha for any given A B. So, for any given A B from the scalar, we take T of A alpha plus B beta. Now, since this T is a linear transformation, this must be written as beta. Now, this is 0, this is 0. So, this will give us basically. So, this implies A alpha plus B beta belongs to kernel of T. So, if alpha, and this is true for all alpha beta, and this is true for all A B from the field. So, this implies by theorem which we have proved in the vector space class that kernel of T is a subspace of U. Kernel of T is a subspace of U. Okay. So, this is also called null space. So, sometimes kernel of T is also called null space and it is written as NT. Okay. So, now we will just have the some theorem on it. So, like suppose we have a vector space from U to V and U V are over the same field and this is a linear transformation. Suppose this is a linear transformation from U to V. Okay, this theorem is telling T is 1 to 1 or injective if and only if kernel of T is only the 0 vector of U. Okay. So, how to prove this? So, it has two parts. One is the first part is it is 1 to 1. If it is 1 to 1, so let us try to prove that. So, first part is suppose T is 1 to 1 and we know that T of 0 of U is going to 0 of V. Now, if it is 1 to 1, there should not be any other vector which are mapping to U of V. So, this implies kernel of T must be only this vector 0 vector, because it is 1 to 1, no other vector should map to the 0 vector of V. Now, the other way around, suppose kernel is 0 vector, then we have to prove that this is 1 to 1. So, this is the conversely, suppose just prove that suppose kernel of T is consists of only 0 vector of this of U, then you have to show this T is 1 to 1. How to show that? Yeah, so we take 2 alpha beta and suppose T alpha is equal to T beta. Let then from here we can say T of alpha minus beta is basically T of alpha minus T of beta. So, this is basically nothing but we know this alpha beta. Okay, so, T of alpha beta is basically so now these are same. So, this will give us a 0 vector of V. Now, we know the kernel is consist of this. So, this must be alpha beta must be equal to. So, this implies alpha is equal to beta. So, this implies. So, T of alpha is equal to T of beta implies alpha is equal to beta, and this is true for all alpha beta like T of alpha equal to T of beta. So, this implies T is 1 to 1 or injective. Okay, so, if the kernel of T is 0 vector, then the mapping is T is 1 to 1. Now, we have another theorem. So, this theorem is telling suppose we have a linear transformation from U to V and over the same field and kernel of T is 0 vector. So, this means that is T is 1 to 1 that is T is 1 to 1. Okay. So, now that this theorem is telling, if we take a, let alpha 1, alpha 2, alpha n or alpha r be a set of linearly independent vectors, then this set T of alpha 1, T of alpha 2, T of alpha n, these are also linearly independent set of vectors. So, if you take a linearly independent set of vector in U and if T is 1 to 1, then it will give us a linearly set of vector in V. So, how to prove that? So, to prove this is to be linearly independent, so this is R. Yeah, to prove this is to be linearly independent, what we need to show? We need to take A 1 T of alpha 1 plus A 2 T of alpha 2 plus A r T of alpha r to be 0 vector in V. And now we need to show that all these A i's must be 0. So, how to show this? So, this implies from the linear transformation properties of T, A 1 alpha 1 plus A 2 alpha 2 A r alpha r is equal to this. So, now this must belongs to kernel of T. Now, but the kernel of T only consists of 0 vector. So, this implies A alpha 1 plus A 2 alpha 2, this is the 0 vector of U. So, this implies all A i's are 0, because these are the linearly independent set of vector in V, all A i's are 0. So, this is the proof. That means, if you take a linearly independent set of vector from U and it will be again a linearly independent set of vector in V. Okay. So, we will continue this in the next class. Thank you.